Hi all, I'm going to redo this problem because yesterday I think toward the end of the class we made a little mistake and I want to fix it and I don't want to use the class time tomorrow, so I decided to do this through a video. So I drew the ring and I instead of using only one small element, charge element, I am using two so that you can actually see the symmetricity better. So they are all the point A is also marked over here, and the center of the circle is there. The radius of the circle is not the circle, radius of the ring is R, and the point is Z distance away from the center, and the axis is passing through the center of the line charge. In this case it is a ring. And then the linear density, linear charge density was taken as lambda, and by definition that becomes q over the length of the ring, which is 2 pi r in this case. So if you take like a small charge versus the length of that particular charge, it is kind of odd to say that the length of that particular charge, but in this case we are taking a small element from the ring which has a dq charge, so that's why I called it as the length. So there you have it. It has the same, basically same meaning. So if you want to rearrange this in order to fit our equations, you can say dq equals to lambda times ds. So in order to find the electric field, we are using the equation that we know by definition, dE equals to kq. In this case dq, that is the small piece, the charge element that we are looking at, and then the distance from the charge to the point is little r, so r square. Now by the right angle and the Pythagorean theorem, you can say that r equals to r square, that is the uppercase R square, and then z square, and there you have it. So I have dE equals k dq divided by r square plus z square. Now you don't have the radical, it's gone. So I call this my equation number 1. Alright, so if you look at the point A, and if I actually bring it down here and redraw it so you have a better view of that. So one way I have, I'm going to extend this line. So there you have one electric field due to one infinitesimally small charge, and then this side you have the other, and there you have the y-axis, and they both make the angle theta with respect to the vertical direction, right? So if you let me call this also dE. So if you look at the there are number of dE electric fields around this cone. I just for our convenience and not to make a huge mess, I only am showing two electric fields over there, just two of those, two electric fields. Now I am taking the components along the x-axis. This gives me a dE sine theta. The angle is with respect to y-axis, and then over here the same dE sine theta. For now I am going to erase that a. Actually I wrote sine theta on top of it, that's fine. And then if you look at the y component, there I have dE cosine theta due to one electric field component over here, and if you look at the other one, that also will give you the same magnitude dE cosine theta. So clearly you can see the x components are like arranged in such a way that when you add them up they all get cancelled out, and the y components are set in such a way they all get added up. So in order to find the net electric field at the point A, I'm going to call E net, and don't forget this is at the point A over here, and then E net's going to be the integral of y component, right? Y component of dE. Now what is y component? Y component is given by the magnitude of the field and the cosine theta. So this is where up to this level everything was good, but I forgot to substitute for cosine theta yesterday. That's where the mistake was. So I'm substituting for dE, that is from equation number 1. So I have the integration, and dE is k dq over r square plus z square. Then what about cosine theta? I forgot that. And if you look at this picture again, the picture down here, the theta angle is the same over here, and then opposite angles of course, and then this if I mark the theta angles over there, that would be the same. So using again the right triangle and the trick that you know, cosine theta becomes z divided by the square root r square plus z square. So this is the part that we didn't have in the class yesterday. So you can take substitute for dq here. So dq becomes lambda ds, and of course the z stays here, and then down here you have everything else. I don't think I can write it here because of the recording part blocks it down here, so I'm just gonna say the denominator is r square z square raised to the power 3 over 2. In order to save some time, I brought all the equations from the other side, and then I rewrote here, and I took the constants out of the integrand. So here you have the integration going from 0 to 2 pi r, and if you remember, we are integrating over ds. Well, if I redraw the ring, the ds element is sort of like the length of this little piece where we took as the infinitesimally small charge piece out of the ring, right? So this is the center, of course. Now we are taking the integrand, and the final the answer is, of course, it's pretty easy in this case, z k lambda. Nothing happens to the denominator, so I am rewriting it. Check out if I make a mistake. And then here you have 2 pi r. Now if you recall, we said lambda times 2 pi r is q, that is the charge of the net charge of the ring. So I am going to get these two together again, and then rewrite z, k and q, of course, down here, z square plus r square and raised to the power 3 by 2. If you want to substitute for k, that would be 1 over 4 pi epsilon naught, and you have q and z there, and down here you have z square plus r square and raised to the power 3 over 2. Now if you are looking at a very large z compared to r, very large z compared to r, then the denominator r sort of like goes away, and leaving you with E net equals to q z over 4 pi epsilon naught and z to the power 3, and taking care of the power and everything. That gives you the final answer, q over 4 pi epsilon naught and c square. In this case, as you can see, the electric field changes as a function of z square. In the earlier case for a dipole, if you recall, you may remember that it was changing as a function of z to the power 3. So I don't know if I want to box these things, but anyway, I'm doing it. All right. Also, when z equals to 0, as we expect, the E field should go away, and if you plug z equals to 0 in equation 2, you will get that answer as well. I think this kind of explains what we were talking about toward the end of the last class, and especially this would answer Alex's question.